Greetings, I'm Mike Wong, and I'm here to showcase multi-wavelength views of Jupiter's giant storms. This is one of a large number of connections between the Hubble Space Telescope and planetary science. For example, Hubble has detected 4 dark spots on Neptune in the years following the Voyager 2 flyby, something that no other facility can do. HST discovered 4 smaller moons of Pluto in advance of the New Horizons flyby and found spectroscopic evidence of plumes on Europa. UV auroral emission has been mapped on a variety of timescales on Jupiter and Saturn, and linked to solar wind and magnetospheric conditions thanks to data from NASA spacecraft like Ulysses, Juno, and Cassini. Hubble has observed asteroid disruption events and interstellar objects and obtained high-resolution imaging of impact events, including in the important ultraviolet range. In 2020, we reported on a comprehensive dataset of Hubble and Gemini 5-micron imaging data during the Juno era. The dataset includes observations collected specifically to provide context for Juno, as well as VLA support and annual Opal program imaging. The images on screen were released in an interactive form by Gemini Observatory and Noir Lab, and you can access their release using the QR code. These observations from January 2017 are particularly special because they are truly simultaneous, although some derotation was needed to line things up due to time delays from mosaicing and filter selection. You can also get to the release by searching Jupiter UV Interactive on Google or DuckDuckGo. That will be the first search result. On Bing, you'll have to scroll down a little bit until you see By Jove at Noir Lab. And on the Brave browser, it's the second hit, again, By Jove. The 5-micron infrared view shows thermal radiation from Jupiter's deeper atmosphere in regions with low overlying cloud opacity. The visible light view shows cloud color and opacity from the top of the tropospheric weather layer down to the water cloud layer. The ultraviolet view shows a combination of UV-absorbing haze, high-reaching cloud tops, and Rayleigh scattering from molecular gas. The Gemini Observatory contains twin telescopes in Hawaii and Chile, so their image release included Spanish notations, as well as English. 3 types of large storm systems can be seen in this Jupiter image. Anticyclones, like the Great Red Spot, are high-pressure systems, similar in some ways to eddies in the Earth's oceans and dark spots on Neptune. Low-pressure systems are cyclones, with very diverse appearances. The brown barge shown here is one example. Jupiter also has large transient convective outbreaks, like the Southern Hemisphere superstorm shown here. These don't have long-term rotation, like the anticyclones and cyclones. Hubble enables very detailed studies of the dynamics of anticyclones, especially the Great Red Spot. Our velocity retrieval code, ACCIV, is available on GitHub and allows us to derive dense velocity vector fields using data separated by 1 Jupiter rotation, about 10 hours. This long time separation gives very high precision with formal uncertainties about 3 meters per second. The velocity field of the Great Red Spot is bounded by a ring of maximum wind speeds, shown here in blue. We found some interesting things when we looked at how this high-speed ring varied over time in a paper that came out this year and is being presented at the 2021 AGU Fall Meeting. It has been known for a long time that the Great Red Spot is shrinking and circularizing based on the shape of its red cloud area. We found that these trends are mirrored in the high-speed ring. If these trends continue, the Great Red Spot would become circular between 2035 and 2040. The data from HST WFC3 cover 11 years, about 1 Jupiter year. We were also surprised to find that the wind speeds are increasing over time. The increase is only about 4 to 8% over an 11-year period, so it's quite small. Without the high precision enabled by Hubble's sharp imaging and the long observational baseline, the increase would have been missed. Our dataset reveals new complexities in the variable outer structure of anticyclones. Using data from the Keck Observatory, of which NASA is a partner, DePotter et al. In 2011 found that most small anticyclones were encircled by 5-micron bright rings, meaning a ring of cloud-free air. Larger anticyclones like the Great Red Spot, Oval BA, and the northern oval shown here did not have these rings. The size dividing the small and the large anticyclones was the atmospheric deformation radius, suggesting a dynamical difference between small and large anticyclones. But our 2017 data show that these 5-micron bright rings are variable over time. The same northern oval had developed a bright ring in our 2017 images, and even the Great Red Spot had an incomplete ring-like structure in its outer regions. We can use the Noir Lab interactive page to look at these cloud-free rings around anticyclones. For example, these ones in the north have fully complete 5-micron bright rings around them, whereas the white ovals near 40 degrees south latitude appear as a series of dark, cloudy ovals on an infrared bright background. It's also interesting to compare the visible and ultraviolet appearances of the anticyclones. The Great Red Spot and Oval BA in 2017 appeared red, while the ovals at 40 degrees south appeared white. In the ultraviolet, their absorption is also very different. The Oval BA and Great Red Spot are dark purple in this UV composite image, while the white ovals appear red, only absorbing in the shortest ultraviolet wavelengths. Our study of the Great Red Spot over time also found surprising changes in a couple of wind field parameters. The wind shear at the Great Red Spot latitude, shown here in blue, and the Rossby number of the vortex, shown here in light red, both shifted their values around the same time as a major convective outbreak. This outbreak can be seen marked superstorm in the 2017 image, and it never came close to the Great Red Spot. The effects seen in the velocity field indicate that these storms are capable of affecting much larger areas of the planet than might be expected based on the size of their cloud features. Data from the OPAL program in 2020 showed another large convective outbreak, this time in the northern hemisphere. These northern plumes are the largest convective storms on Jupiter, and they occur on its fastest westward blowing jet. HST maps provided context for ALMA millimeter wave observations of the 2017 storm in the southern hemisphere. ALMA brightness temperatures near 1.3 millimeters are mainly sensitive to ammonia concentration, so the ALMA data indicate enriched ammonia gas in the storm outbreak core with subsidence in the surrounding area revealed by depleted ammonia gas. Juno passed close to the storm on its fourth orbit. Its microwave radiometer actually sampled the region to the east of the storm core, where Gemini 5-micron maps showed a clearing in the clouds. The white star indicates a microwave anomaly detected by Juno. Here's the Juno data. The red trace spikes up at the location of the star in Juno's shallowest sensing channels. This means that the radio brightness temperatures were higher for this fourth orbit compared to the average shown by the black trace. High brightness temperatures mean depleted ammonia surrounding the storm core, consistent with what ALMA saw. Juno also detected lightning in the storm vicinity, shown here by little blue disks. This is a sign of active moist convection. On a different Juno orbit, lightning closer to the pole was detected by multiple Juno instruments, the microwave radiometer and the WAVES instrument. Hubble data in this region showed what we now recognize to be the three-way cloud structure signifying active moist convection. High, thick cloud towers, deep water clouds, and cloud clearings. A long feature in the north called a brown barge is an example of a cyclonic vortex or low-pressure system. The Noir Lab interactive page shows the diversity of cloud structures within cyclones. Cyclones, called folded filamentary regions, have lots of chaotic, fine structure, suggesting active moist convection. Thick clouds appear white in both visible and UV images, and they're mixed together with clearings that show up as an array of bright points in the thermal infrared. Then there are cyclones with smooth edges, like the brown barge in the north, or this almost invisible feature close to the edge of the disk. This one is known as the South Temperate Belt Ghost. In fact, even though these cyclonic vortices look so different from each other, the same cyclone can morph from one type of appearance to the next. Juno snapped some close-up images of the ghost in 2017 during Juno's 8th orbit. It was nicknamed the Ghost because it can often be difficult to see, particularly when Earth-based views lack the high resolution of JunoCam. Inurigato et al. In 2019 published an analysis of the ghost cyclone, catching it in a time series of images as it transitioned from its quiescent, hardly visible state to a more jumbled and chaotic state suggestive of active convection. The transition was marked by a particularly large storm eruption. New Horizons, when it flew by Jupiter in 2007, detected 2-micron ammonia ice spectral signatures, shown here in light blue, along the edge of a cyclonic vortex. These spectral signatures quickly fade, so they may be found only where the freshest ammonia ice is found. JWST will be able to detect 2 and 3-micron ammonia ice signatures with the NIRSPEC integral field unit, if fresh ammonia ice is present near the Great Red Spot or in clouds close to the South Pole. Hubble continues to make new Jupiter discoveries by connecting with data from other observatories and the Juno spacecraft. Feel free to follow the QR code to NoirLab's interactive images and see if you can make any new discoveries of your own.